Good morning, everybody! Woo! How are you? Yeah. So yesterday we had like a bunch of fantastic music competitions, and today what he will show up, it won't be like a black magic. This is like a shaders for beginners, like for your beginners. I already saw Mako is a professional lecturer. He will teach you this in a minute. Right after that, you sit down with your laptops, you do a demo for next year, okay? Yeah, that's not very long. No, I'm joking. So everyone, please give a warm welcome to Mako.
Welcome everyone. So my name is Floppy. I'm here to teach you shaders. I see many coders here on the audience, which are not very welcome because this is for beginners. But hopefully I will introduce those that didn't see shader toy for your eyes, or you are like when you finish this lecture, you will be able to start your own work. So by this, after I defined this one, I cannot go very far. One knows Inigo Quiles, who is, of course, this is from his one of the very first talks about shader coding. And why do I show this one? So not this one, but the slide. So I show this because this is. Let me just change the. What is happening here? Okay, so why do I show this one? Because this shows the very fundamental thing. So how shader work? Shader is a program, is a computer program that is calculating the picture. So of course, this is very simplified view on shaders in general, because in general shaders are the part of a graphics pipeline and they are of different kinds. But what we will talk today is about the demo scene application and how the shaders are used here. So what we will use there is called pixel shader. This doesn't really matter in 2022, because if you learn pixel shaders, you will immediately learn how to program compute shaders, for instance. So you will be able to, for instance, program the entire pipeline by your own. But let's think about the picture. So the picture is a group of pixels, okay? So it's obvious, but this is important to remember that each individual pixel in the picture will be exposed to the same computer program. What does it mean? Pixel shader, in the way we will be using it, is run on each pixel individually in parallel. That means that the obvious and the simplest shader we can write is the one that is filling out the whole picture with the same color. Okay? So let's do it. Okay? I will just now jump into practice and let's write a shader that is filling the entire screen with a color. So what you see here on the screen is a program, web program, done by IQ, the author I showed you before, which is used to actually run shaders in web environment. So for those that are worried about, because I talked to a few of the people before the talk, and people asked me, so you will show shaders, but will you show how to run shader? No, I will not. This is super simple, and this is just technical thing. After you learn this one, you can copy this shader and just run in the exe program for 4K intro. This can be another lecture, but this is more for like a technical stuff. What you see on the right-hand side is like a fragment of a program which is now empty. Let's not go very deeply into details of what is passed to the shader because we will use it in practice. But this is a program. So whatever we write here on the right, 1 0, 1 0. Okay, I cannot write like this, but let's say it's equal something like this. So if I create this C and now run it, okay, you will see white color. Why? Because I put 3 values, RGB, this is red, green, blue, okay? So now that means that if I put this one, for instance, red 1, blue, green 0, and blue 0, then if I run it, I will have a red color. Again, this is very simple, okay, in principle, and what I did, I ran this shader again at each individual pixel. So, why is it important? Because now, for each individual pixel, I can run a little bit different code. But how to implement code, actually means coordinate of the pixel, let's say here, and let's say that I will now read it, so this is vector which is 2-dimensional. Let's say this is position, is equal to frag chord, okay? So now if I have this, this is my coordinate in the resolution of the picture. So if the picture is HD, so this is from 0 to 1280 or something like this. So now to make it from 0 to 1, because this is how colors work, I want to divide it. And I divide it by the, let me read it because I never remember by heart, resolution, okay, dot, and now I can take only X and Y from the resolution variable. Now, when I do this, my P variable, so now if you are not a coder, let me do it larger, this will be maybe, good for lecturing. Now, if I write this line, that means I read my frag coordinates, so my coordinates of the in the picture, and I divide it by the resolution. That means P has 2 components. One is X from 0 to 1, and one is Y from 0 to 1. Okay, so now if I have P, which is from 0 to 1, let us write P.X. If I do it, now you can imagine this will be like a gradient, okay? This gradient is created because this program was run from left to right in each individual pixel, and for instance, this pixel has a chord. He remembers from Amiga Demoscene times when the what was the name? Chunky to planar was introduced. Many people has started doing effects like 3-dimensional tunnels or distortion of textures and stuff like this. And many demos was done. So I remember one demo from myself was done only with this technique. It was released in the party in Czech Republic and it won. I remember there is one famous... Yeah, tune in, tune out, drop out. So this demo you can watch, and it was done with this technique. But nowadays, one can do with shaders, and this is really very cool because you can do very high resolution. And Shader Toy is a fantastic tool for doing that. So now let's move on. So I have slides, but I prefer to do as much practice as possible at this point when you are still listening to me and you understand everything and you say, this is so simple, come on. So very good. So now let's do something also simple, but let's use the second coordinate of P. So P.Y gives you also 0 to 1, but this gives you, Y coordinate change. So this is gradient in Y direction. So now we see kind of a start of, I don't know, what effect can that be, but like a plasma or something, okay? If you use some sinuses or cosinuses. So let's improvise a bit. I didn't think about doing this, but if we do sinus, from 0 to 1, so multiplied by this and maybe times this. Okay, now I do an error. Don't afraid about this, what happened now. I did it on purpose, but this is for you so that you can see how errors looks like in Shader Toy. So Shader Toy is not really very much of a toy. It's a kind of a serious tool, and one of the features it has is to show you what errors you do in your shaders. So here, for instance, I used the wrong operator types, no operation multiplication, so I cannot multiply, because on left-hand side of my multiplication, there is a floating point number, so the number that is from 0 to 1, whereas on the right-hand side, there is an operand that is const int. So this probably means that this 2 is wrong, because I cannot multiply integer number by floating number. So I have to, this is a coder's detail, but one has to take care and just write 2.0. If you were coding in C++, that would be not like this. That would be much easier. So now we have this with a sinus. So
Any difference to multiply times 2 times 3, 13?
of course,
Multiplying times 6, 28.
no problem. You mean this one, like this?
No, if you actually 2 times 3 is 6, 28, right?
Okay.
Is any slower or is it optimized by shader?
Fantastic question. I cannot answer this. I have no idea. I mean, I don't know what is the very detail of shader like optimization at this stage. I suppose Zahir will know. Yeah. You're welcome, please.
Actually, it's a simple matter. So the shader compiler is built into drivers, into the graphics card drivers, and the compiler will optimize that out. So it will do the constant folding, and it will just, at the optimization stage, it will multiply those and put the final value. No difference at all.
Okay, so now another feature of Shader Toy is that it exposed, for instance, the time of your system. So you can use the time to make it fun. So let's make some like effect, okay? So a very simple effect would be to use the time to change properties of the sinus. If I change it, then I will start doing like a plasma on screen. Okay, so if you click this question mark here, you will see some variables that are built into Shader Toy. And believe me, if you are a coder or you want to do it, it's of course you have to spend a little bit of time or have some coder friend to do that. But you can do very simple copy from this to like an exe file again. So now, what can we use here? So there are some functions that are built in, and most of them are the standards for the language that we use. There are some language details about the language that we are using, so you can use it as a reference and search for some useful functions if you want to find something. There is some how-tos and Shader Toy input. And Shader Toy input gives you an input from user or from the system. So you can use, for instance, mouse position. You can use the channel time, the current time in seconds. So let's use iTime. So iTime will be floating point number, and this is current time in second. Okay, in seconds. Let's use it, iTime. So we will use iTime to change the sinus, and this will be iTime and multiplied by this. So now its sinus is moving. It's a little bit too much. I think it's, yeah, animation. Now we have the animation here. We can use this iTime for many other things. So we can use cosine, iTime, dimes. It's completely improvisation now. I have no idea about the outcome, but okay, let's, yeah. So we started already doing some little intro. And if you are clever, so not clever, but if you want to do it quickly, and this is actually what I do for my intros, so don't hesitate to do that, you can Google, very nice thing. So this is a hint for those that want to really code something. So you can take this you can take this shader and you want to do 4K intro with this. Just put your music and so on, yeah? So in order to do that, and I know that this is the most interesting because this gives you a hint how to become a coder, okay, these days. And this is that simple if you are accepting this level of complexity. So go to Google, accept everything, and then Google Inigo Quiles. And his impact on demo scene is very large, not only because of shaders, but also because of another thing he did. Code, website. Again, this website is pretty cool at all, but I will not show you anything more than the super simple intro systems that is made by him. You click code, and there is a demo framework. If you click here, you will have a list of the framework that he is maintaining for years already. So if you want to do 4K intro for PC, for instance, then the immediate place to go is here, because you can download Visual C++ framework for 1K intro, 4K intro, for 64K intro. And now I am, of course, a coder that has made many of things like this and on Amiga and on PC, but I also use it. Why? Because doing that, what he did here is like opening open doors. It's stupid. Much better is to concentrate on shaders these days and do really fancy shader. So don't worry, use this. If you can do better, then do it. And the best is to release it. But what he did is here. So now we can actually do a 1K intro for this particular party if we want during this talk. That would be actually very nice. Yeah, not really. It's afternoon. Yeah, but if you talk to these people, you can do so. Anyway, so pixel shader. Now we know how to start. Now, again, just to recall, now you have the practice. You know what does it mean that we do the program for each individual pixel. Now this is the main algorithm, and it's super simple. And this is how it worked on Amiga. We were having the chunky to planar, and we did exactly the same. One function which was run for each individual pixel, but not in parallel. So why shaders became that useful? Because these days, this computer, the GPU that is in this computer on the graphics card, is a very powerful tool to run thousands of these programs in the same time. So this is a vector machine that is running the same program just like this. And this is why many coders are these days, there is a possibility to create a ray tracer in real time, in full HD, on an ordinary PC. This is really super cool. So now this is what is happening. So for each individual pixel, the program is run. And now I will split my talk into three parts. First of all is a very simple technique to create shapes in Shader Toy. I call it Shader Toy, but that is really more general. What we are doing here is GLSL shader coding. So Shader Toy is, again, a tool. And first of all, we can do shapes. And shapes are important because with shapes you can do vector graphics. And this is also opening doors for very nice effects. The second is deformation. And this will continue what I did already in practice. And then I will tell you a bit about ray merging, just to not leave you with the most basic techniques. Ray merging is one of the most common technique to do 3D in shaders, and I will tell you why. It's also a very interesting subject. So I will not open all these shaders. You can do it later after the talk. I can pass the talk to everyone just to show you a few pictures what shaders can really do. And this is an example of a shader done with a distance function, where the distance function is used to create shapes. And this is a plane deformation example, so typical like a tunnel done with shaders and mapping of the texture coordinate, and ray merging. And this is the subject, as I told you, about the algorithm that is well suited for for shaders and parallel computation. Now, why Shader Toy? Shader Toy is done by Inigo Quiles and Paul Jeremias, and IQ was developing this in his spare time. He was also working at Pixar and so on, so you probably know him well. It's a WebGL application, so when you run it, it's run on your PC. So this is not like you run in the cloud. You are writing program, but it's run on the client side, okay? This is how it works. So you need to have a decent GPU, but these days, each laptop, actually on my mobile phone, I can write shaders without problems using Shader Toy. It works pretty well. It became also database for shaders, so you can have thousands of them. And it's a source of inspiration for many people, and this is actually what IQ is suggesting to do. He also suggests to copy shaders from other people, fork them, just to mention the author, and develop, because they want to develop community, and it happened. There are people that are doing crazy stuff. I don't even do 5% of some people that are doing on Shader Toy, because, so there are famous coders from old Amiga and PC demo scene that are doing such a nice things that, I don't even know many of them how they work. And you can learn a lot from them, and of course, not only very simple. This is the first version of Shader Toy, but now it's more advanced. I will not go into details of this. This is Shader Toy we are working with. And again, just to recall, this is a database, so you can open your profile and you can create shader, save it, publish it. It works more or less like YouTube, but it does not have any advertisements in. So it's more like demo scene, people here. What are alternatives in 2022? So before this talk, I asked on Poet, because I don't really know what people are using these days apart from Shader Toy, and they didn't really mention many of them. There are some tools I know also, but they are not that useful. But people mentioned Polycube and GLSL Sandbox. GLSL Sandbox is, I will show both of them. They are interesting to see. GLSL Sandbox is again a website that is exposing shaders that you can just open, and when you open, they are here, and they are here with code, and the code you can change. So whatever you do, you can run, and on live you can edit. It's interesting because you can live code. And the other one is Polycube, and this is more advanced tool. Because the Polycube doesn't really contain of shaders itself. It also contains of some OpenGL code that you can mix with shaders. And this is interesting because then you can do really like parts of an intro. Of course, this would be doable in Shader Toy as well, not a problem. Yeah, but anyway, you can have OpenGL and Shader Toy. GLSL shader code as well. Okay, let's move on to some examples, and first of it will be about shapes, and this is first shader that we already have. Hopefully, you can see on the bottom of the screen there is code that is creating a empty screen. And now we can, of course, change colors. This is obvious. So to change a color, when you have this should be, of course, red, not black. Very simple question about. Very good. This is a distance. Yeah, this is a distance from the point 0.5, 0.5. This shortcut 0.5 just means this is a vector with the same coordinates. So now if we do this, that means that computing this variable, we will know at each individual pixel what is our distance from the center. Okay, so let's not talk too much and move on to the example. Let's close this. This is our gradient. So I will now do this, the same that we can do in C++ on C. We can basically comment out fragment of the code, and let's calculate distance. So that was what? Float dist okay, let's call it d, so that it's shorter, is equal, and now this will be length. So this is a built-in GLSL function. Length means the length of a vector, and now our vector will be p minus vector of two dimensions, 0.5. Okay? Okay, now we have a d. Okay, let's write like this. Now, this doesn't mean anything yet, but this d number will go from from 0 in the middle to like, I don't know, 1 on this edge and something more than 1 in the corner. So now let's use this d for a color. So now let's create the variable color. Vector 2c is equal vector 2, and let's call it d, and 1. This fourth variable is just alpha, okay? We can increase and decrease alpha. Red, green, and blue will be taken from the distance from the middle. Now that means that we can do that. D. Okay, we don't have to do... sorry, why don't you correct me? I was wrong. Vector 4 is this, and now we can frac chord, and we'll see as a color. Now, this will be a gradient from the middle to the edge. Let's run it like this. But I don't like it because it's black in the middle, because the distance from 0.5 is black in the middle, and it's white on the outside. It's much better if we use this, 1.0 minus, sorry, not in this point, this would be wrong. Of course, I cannot do this, but I can do 1 minus length, okay? For a light, so it's like a light. Now I want to enlighten the texture at some point, so that's why I'm doing this. But let's create a variable that will have some coordinate that is moving in time. So let's say this is like some point, so will be two-dimensional. It will be, let's call it point, and it will be equal to, and now will be vector 2 sinus I time. So from -1 to 1, and the other will be sinus of time plus 0.4, for instance. Okay, this will be our vector. Now time is not declared because I didn't use I. Okay, now this works. Now I have a point that I can use to move the center of our light. So now will be p minus plus and point. Now it will be moving a little bit like in a circle. It's a little bit too large, so I can multiply 0.3. Okay, now it will be like that. And now if you have a dynamic music, like yeah, so you want to make it faster, so you can multiply I time, like here and here. Now it will be more. Okay, okay. So more or less now you know what I want to have. So now we have the second effect. Yeah, it's maybe not of the highest quality. The highest quality comes with textures. Textures are nice because you can color very nicely, and you don't have to be a coder. These days you don't have to be a graphician as well. You can use Midjourney and create nice textures. And okay, but it was supposed to be with about shapes. So let's move on with shapes. Where is it? It's here. Okay. So how to create? So this you know. Now we have a gradient, and this is a mixture of what I did just now, because this is the same technique with a distance. So now to make a nice shapes, you can use a built-in step function, and this is a very nice function to use for like a vector graphics. It's a function that maps your variable, so you can have a variable in each coordinate system from 0 to 1 or from whatever, to a step function. So to the function that gives you 0 here and at some parameter gives you 1. But the built-in property of this function is that it is moving you smooth. So it can move you smoothly from 0 to 1. And this is how the step function can be used. And let's write down the very simple function to create circles in Shader Toy. So to create a circle, we will create a function that takes the coordinate, takes the vector, and takes the position of the circle we want to have, and takes the radius of the circle. And what the function is returning, it returns the step function that goes from 0, so it gives 1 from 0 to r, so to this variable r, and then 0 if the position is larger. And we will use the length, so the function that gives you the distance, to actually change the value of this step function. And with this technique, with this technique, you can basically create sharp edges. So, and they don't have to be very sharp, they can be smooth. So by using parameters of this step function. And this is what you can create. So you can use a sharp step function, you can use smooth step. So smooth step has an additional parameter, and this tells you from which point to which point there is a transition. And by using this, you can have a smooth circles. And then you can use some variations like arcus tangens, just to make the changes in depending on the angle. Okay. Okay. And these are examples of smooth functions used to create graphics. There is an example of a simple circles, but made with nice colors, and this is really a nice example of how to execute such a simple techniques. And this is the one I showed you already. This is from IQ, and let's open it, because IQ is one that one should go first if you want to learn. And this is an example of vector graphics that is scalable. You can basically open it in any resolution you want. So if I open it like this, oh, this is a very good laptop because it opened without any problems here. And this is a code. It's a little bit larger, but it does not really contain much different techniques. This is a technique, and this is my picture done for revision when I had some little children that liked Peppa Pig, and I will open it not to show you the best way to do it, but to show you the technique. And the technique is basically that you create these distance functions like this circle flower, yeah, that shows you and what I discovered doing this picture was that whole Peppa Pig is possible to be done with ellipses. This is crazy. One can really draw it. I mean, yeah, you can do another Daddy Pig, for instance. But all of these are circles and ellipses. There is anything else in Peppa Pig. It's amazing. So you wouldn't need anything else than ellipses here. Okay? So you can have fun. If you have children, you're welcome to play with this. Actually, my children were playing, so these are examples of my, children creativity to, yeah, Daddy, can you add another Peppa Pig jumping with ball and stuff like this? 3 years old. Yeah, I know. Okay, and there are better examples, of course, so the IQ was showing hertz and so on. But I want to move on. So this is the first technique, and the best way to work with this technique, because now, I could really try to now rewrite the code and do, but this way we would progress to 2 circles, and that would be everything, because I would do many mistakes, because it's getting more and more complex. But let's move to the second technique. So hopefully you will have a clue how to use it. And this is deformation. Deformation technique starts with texture, and now I will move to the practical part because I want to recreate this program first. So what I will do now, I will take my coordinate in the picture and I will grab a color from the texture. So now imagine you are in the fragment program and you know what is your position and you want to copy the texture color from the texture from the place that fits to the screen. So for instance, if the texture is the same as the screen, it's very simple. Because then you just copy the color from the same coordinate like in the picture. Okay? You can change it and this is the way the effect will work. So now let's move on. And this will be, so this will be commented out. Okay? And our program will look like that. Okay, it's our position, and this is our color. Sorry, okay. Okay, so this will be our color, and now our color, this function is called texture, and we will take the texture from the channel. There are 4 channels. We will take the texture from channel 0, and this is the one that is on the, here. This already has a texture, hopefully it will work. So now let's take it. So our function is texture. This texture will give you 3-dimensional vector, which will be a color. And this texture will take two parameters. First is a channel number, and the second is coordinate in the texture space. So the first will be channel I, channel 0, and the second will be coordinate, and I will just use P. P is my coordinate in the screen. So now keep fingers crossed, because if something doesn't, okay, oh, okay, so errors are, this happens always, you know, I always tell my students that during my lectures, because I use live programming for the lecturing on the fundamental subjects on programming. It always happens, and the best lecture is when it happens, because then I can learn also, but they then can learn that even I do mistakes. I do a lot, and even with simplest things possible. And I don't remember many things as well, so I have to read and use documents. 4-dimensional vector, so I need to use this time. So, for instance, we can multiply P. This is, let's say, we will make it nice way, so we will add another variable. This is modified P, so vector 2 modified P will be equal P times, and now we will multiply our P by some variable that is moving periodically in time, so the best is sinus. And the best would be sinus plus 1, because sinus is of course minus, which is not good. Okay, like this, and this will be I time multiplied by 0.2, and now, okay, and now this sinus, okay, let's see what is happening. Now this will move in and move out, but it's too slow. It's not very nice. It will be much better with this. Now it will be like a zooming effect, but this zooming effect is not nice. It would be better if we multiply here. So you see, it's very nice for prototyping, okay? For this, okay. Now we have zoom effect, but this zoom effect is not very nice because it's zoomed to 0, 0, it would be better to 0.5, 0.5. Question?
Where is the code for loading texture?
Okay, this is a very good question. There is no code for loading texture. We are starting from a system in which the texture is loaded. But if you have a difficult doing that, so you don't know OpenGL or something, then I recommend to go to this IQ demo framework. Then you are exposed with the same in C++ code.
Do you know if this texture is passed to the shader through constant buffer or maybe something dynamic?
Yeah. Then you can change it if you recode it, of course. Yeah, but here it doesn't matter. There is, and this should, of course, 0.5 I time, for instance. So we will move around and zoom, so it starts to be like this, okay? Now we can use it to deform, and this is pretty interesting because we can use our UI coordinate, I mean XY coordinate, to map with another function. This was all linear, so we just multiplied. But how to do it, let's move on here on the slide. So now we will modify position, and we will modify by different things. So first of all was this. I already did that, so I used planar mapping with multiplication of the coordinate position. But if I use another function, like, so this is interesting function, so we can calculate the distance first from the middle. If we calculate distance from the middle and use this distance just to divide our UV. So let's do it. We will not move the texture yet. We will do another one. So we will calculate the distance, d, equal, you remember, length. And this was p minus vector to 0.5. Okay, so now we have this d. MP was not declared. Now let's make this MP. 2 MP is equal, and now we will use d. This will be p minus divided by d. So if I calculate something like this will be another coordinate, but it will be like mapped by another function, mathematical function. So from this point, we will not go directly to the same point, but we will use function 1 over d to calculate something further away. So that means we will move close to the center, and further away, like far from the center. This is very basic for computer graphics, but yeah, something like this. So now if we have this function, we of course can make another thing. We can move in time. So if we copy this part of this function and move here, then we'll have something like this. Okay, it didn't really make yet a nice effect, but this is what happens. Now we will, okay, and so this is one. The other known from the Demoscene times is absolute value function, which we can use to calculate the distance, but for only one coordinate. So we don't do a distance for x and y, we do distance just for the y coordinate, and then that gives you this effect of, so let's make it, float d is like absolute value, yeah? Absolute value p dot y minus 0.5, and now we'll have a function like this. And moreover, we can use this distance just to multiply our c, the effect, but it was not done with this technique, but anyway, it is similar. But anyway, so let's now move the texture a little bit. So if we now use this to move with, let's say we have this, not MP, but this will be move, and the move will be a vector that moves us with sinus and cosine, something like this. Okay, this is a sinus, am I right? Yeah, this, and now we can move our texture with this MP, move. Okay, and now if we do this, okay, I'm wrong. This is the wrong place, of course. This is MP plus, and this will be MOV. Okay, but this function is super slow. What is happening here? This is MP plus MOV. Maybe let's do like this one. Sorry, something is the same, so that you don't see that I'm. This is just moving at the beginning, so that it's in the middle. That's why we are using this first introductional mapping. Then we deform, And first of all, the y coordinate is moved, so I will now comment out so that you see the same. We do the distance first, so the distance is absolute p dot y minus, let's not make 0.8 but 0.5 as it was in the original one. Now we have the uv is equal to p divided by d, so 1 over d function, and then this is this is what I wanted to have. And there, this is again I time. So now we have our first, this is the one I wrote, yeah? And I wanted to add the time here. So this is the something that we can do. It was my first Demoscene demo. Who remembers the demo profanation from genetic demo group? Anyone? That was a demo I was coding based on, so I was learning and coding with my own codes and using codes from Alien. Alien has ripped off an effect from the factory from, what was the Farlight group, and this was a planar mapping of this effect on the right hand. So I didn't know how it worked at the time, really. I didn't know the function. I knew the technique, I knew how to code it, and I learned together with Alien how to create an effect.
Actually explain what function to use?
Yes. So, because Alien was an IT student at the time, and I was a teenager trying to code, and he was teaching me a little bit, but this effect was always based on a texture. What I did was by accident, and this is the most interesting thing on Demoscene when you do it by accident. By accident, I put a texture which looked like on this talk, okay? So by accident, I used this texture. So if you apply this color gradient, the one you used to fake funk, okay? I used by accident, I put on this planar mapping with this ball. What happened was that the texture was copied 4 times. So one was, this was really nice effect. I don't have it here, but you can later watch. One was here, the other was there, here. And then the copies were on the ball. It looked like lighting. It was like a light effect. It was so cool just by an accident. And yeah, I love it about the Demoscene, but now let's see the ball. The ball is also nice, and now I rewrote it, of course, in shader toy because it's pretty simple, and it looks like this. So it's an effect. So if Alien were watching this lecture, he would probably smile here, because this is the effect that we played a lot with. So it's a planar mapping. It's just a quadratic function. Instead of 1 over d, you do 1 over d squared or 3 times d to some power. Basically, here you have this mapping. This is d squared for the middle, and for the outer, and for the middle you have some more fancy mapping on UV to your texture. There is a square root you have to use to make it a circle. It's not perfect fisheye, it's more like a faked sphere. And that was how Amiga was doing it at the time. Okay, so now we are moving, we are moving till the end. Now the question to you, can we make it 5 minutes more to just introduce remerging? We can do even more. I can sit here and talk a lot, but we can also talk in the garden with beer. No problem. We can take a laptop, code something. These are another examples of typical effects. One can do really nice demo with this planar deformation anyway, and I really recommend to make some fun with this technique. Now, ray merging, and this is really, really very nice. Thank you. If you do it after what I say, then no, it's actually very nice algorithm, very simple for very beginners, because there was a time I was a coder, and I remember I was Amiga coder, and I didn't know how ray tracing works. I was a teenager, I was trying to understand more and more, but ray tracing was like behind the wall. Today is completely different. And I don't think this is because now I'm in the different place and I coded a lot, but also because the documentation is everywhere. You have a lot of tutorials, you have a lot of new techniques. which are simpler, and this technique is so simple that one can really use it to create decent productions. One of the production which is using 100% this technique is Salt by Loonies, one of my favorites. I watched it live on Breakpoint, and this was really like, wow, how did they do it in 4K? It's not the best one these days, but anyway. So what you can see is just a ray tracing of some primitives, and and the technique was the one I will now tell you about. Okay, some interesting stuff about Salt, but what is ray tracing? So the fundamental of ray tracing is that you again want to create a picture. So in your picture, now you will not map from UV texture to UV, from the position in the screen to UV texture, but what you will do, you will calculate the value of a light that is in the point that you are hitting using your camera. What does it mean? Because you have to invert your thinking. It's not about doing light, it's about seeing things. So imagine you have an eye, because it's much more understandable when you don't think about an algorithm, but you think about how nature works. Now imagine your eye has some, how do you call it in English, the siatkówka, yes? Retina. And retina is exposed to light, so whatever light bounced off some surfaces is going to your eye, it goes to retina, to the very little pixel on retina. Now I'm not biologist, but I'm physicist, so simplification is my everyday life. So now we simplify things, okay? We have retina. It's like screen. It's like a screen on which the light is going from your scene. Now you are my scene. Now Mikles is my first object, the most close to me. Now what I will do is I will hit Mikles with a ray. Okay. So we take 1 pixel on my retina. And I say, I will hit in this direction. This is direction I'm looking to. Now, what I want to do is now I'm asking a question this ray merging algorithm is answering. I want to find the closest possible object in my scene. And you can use many algorithms for that. The classical ray tracing is about finding intersection of a ray with objects in the scene. But this is not classical, what I will tell you about. The classical is that I hit a ray, so it would be very nice to have a laser point, but I hit a ray and this ray goes there, because I know that he is described by some mathematical function. But now, imagine that I want to do it quicker. Because if I want to do it classically, then the most normal algorithm would be to check with this one, compare distances and say which is sort, and then say which is the closest one. But there is a better technique. Imagine that my whole scene is described by a mathematical function that says what is the distance from the object. This can be done with the simplest objects possible. So for instance, with spheres. Spheres, because it's like a circle. It's just a length of a vector. So if Mikles were a sphere, sorry for using you, but you are the... Okay, so if we assume he is a sphere, and he is in the XY position, then in each individual point in the scene, so here, for instance, the distance is just a distance between the middle and my point. The distance between him and is this, okay? And so on and so on. If his radius was larger, then the distance would be from his surface, of course. So there would be a variable r that says what is his size. Now, this is only a sphere, but there can be also prism described by this mathematical function. So these functions, the distance functions, is the fundamental of ray merging. So if I am able to describe my scene by the distance functions, then what I can do is to assumption that if there is an object that is the closest one, I can do one step, and this is ray merging. I merge over the ray. And this step was of the size of my closest distance. I can omit him. I can do another step. He is again closest, closest. He's closest, but I will not hit him. I will hit you at some point. But this is only because I was like ray merging along a direction. So I omit everything that is close, but I don't hit. And I hit some point. Now, how the other part of the algorithm works. So if I can find an object that I can hit, then, and this is very quick, so this is why it's very useful for demo scene, because the like sphere tracing, so the tracing the closest object, is useful to find thousands of these intersections at second, and then what I can do, I can hit my, so now I'm the algorithm of ray merging. I'm doing the first hit, so I go to him, he will bounce me, I will bounce again, 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 and then I go to, for instance, here, where there is a light source. That means, how many hits I had? I had like 4 hits. That means there will be some pretty light color. But if there were more hits, that means that, for instance, 24, that means that my like travel from my retina to the light source is this constant steps. We are doing sphere tracing, so that means the steps will be larger. Now, this is how we move along a ray. It's a very simple mathematical equation. It's very fundamental. So we have the direction, we have the starting position, and we have t, which is dependent on our distance in the scene. Now, we find so now this is the most important function, because this is a function that finds the minimum distance to the scene, and the whole magic and whole like pictures of IQ is hidden in this function. What he is doing, and not only him, but many people that are using sphere tracing, is to create mathematical function that describes this scene. So for instance, they take some sphere, they take, I don't know, some noise, apply the noise to the sphere edge, and so on and so on. And adding this, one by one, you can create very complex things. And this is how ray merging works. So again, this is our object, this is our retina, and this is our ray. And now we will do first step. So this is my areas of science. People use it, and yeah. But anyway, so sphere tracing works like this. There is a distance. That means nothing in this circle is around me. That means I can move wherever I want along this point up to this distance. Now I can move up to this point. Look how many steps I omitted. Normal merging goes like this, 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 this. This sphere tracing gives you that far in one step. Of course, there are some problems, because if you are close to some objects, then you will do little steps that are but there are also optimization strategies, so that probably KK would tell you more about when he wanted to make more advanced lecture, but I will not go into details. This is not interesting. More interesting is that we can hit the black hole. Logic is here, because you just need to have your XY, and using this XY, you are applying this distance function, and with this, you are doing your ray merging. And that's it. And I used it for several projects for demo scene. There is a 4K intro from myself and so on, and I really must say that this is pretty fun. But there are also other things I like to do, so I didn't really recently did sphere function. There was one intro I used, and I really discovered the world of ray tracing, because one, with this technique, has a lot of fun with prototyping. Imagine that you are sitting in front of computer, you can change some properties of materials and so on, and it really works like on the fly. You don't have to render it. I remember from Amiga, I used Ray Tracer Real, and I was sitting like half a night to see my bathroom rendered, and now I can do it on my mobile phone. This is amazing. Okay, there is a paper, scientific paper. We are at the party under science subject, so J.C. Hart is the first paper. Sphere tracing, simple, robust, anti-aliased rendering of distance-based implicit surfaces. SIGGRAPH 1993. Come on, this is 1993. and the technique was there. This is what science about. And then we discovered it when there were these GPU machines, because this is where this really catched. I wonder if there was anything like this before GPU era, but I know that IQ popularized it, and he is like a specialist now. So let's see a simple ray tracing of a plane. So now you can see we immediately have the Pixar style with light on the floor. Now we can put some object. This is the function we are using for distance, nothing else, just a distance from like a planar. Okay, we have a distance of r multiplied by normal to the surface minus some d, which is the implicit function for a plane. There is an implicit function for a ball. I'm not a specialist on implicit functions, really. It's just a distance from a ball, from the edge of a ball. One can, of course, become a specialist in creating distance functions, which is really good, because I will see what people do. This is amazing. And all of this is just a distance function. I don't tell you anything about multipass shaders, because this is another story and it's not really that interesting. Actually, IQ was trying not to let people do multipass shaders in shader theory for a long time. He wanted people to make single pass distance function stuff only, but then he accepted community wanted this. But still, this technique is the most fundamental. Now this is a ball with radius r, it's with a light, and we can do mixing. If we sum it, it will be like this. We have a ball and we have a plane. Not very nice. This is just a sum of two implicit functions. But there are people who are doing magic with implicit functions by doing some smooth transitions. You remember smooth function? So you can use this smooth function to make a smooth transition between one and the other. But this will not do, will do shadows. Shadow is something that can be computed from the answering the question, what was my way to the light? If I hit a light, I can count how many times I have crossed some object, how many times there was an object that was close to me. And if I count it, I can use it to decrease the light. So for instance, you see, if there is an object moving towards the light, it's like hiding the light from me, yeah? So exposure is less. And this is the fundament. Now we have this the same with soft shadows. So if one was trying to do it in an old style, not ray tracer, but even with ray tracer, that was not that easy, because ray tracer didn't really answer the question what was the way to the light. It's much easier with sphere tracing, and also, so of course with raster graphics, that would be really, really very hard to create. Okay, so now ray merging in pixel shader is the same as the techniques that I showed you before. So we compute the same algorithm for each individual pixel, and there is a code, okay? There is a whole code that is creating this picture. And this is a code that doesn't look that short, but believe me, it's very simple in principles. So anyone wants this presentation, just ask me. I have this stick, I can copy it for you. So we basically have a distance function that is here, and this is the whole distance function, okay? And the most important is the algorithm, which is here. There is some introduction of camera, so that I put some camera. Mapping here is very simple, planar camera. And then there is calculating the main algorithm that is using the function that is here. And this is the function f, which is the distance. And then there is lighting stuff. Just I use the information from this algorithm to calculate lighting. And then starting from this, you can create whatever world you want. And now just to give you some example, there are some cubes. You can, for instance, this is from some paper. I just took some paper from a few years ago. People in computer graphics are using implicit functions, and this is example how to make the cup, okay? Cup is not maybe very fun for the demo scene, but this is all, and now just to show you how this works in, I don't have like the main, I have a very nice effect that I didn't show anywhere, so you can see it was very simple with shaders, because what I did was I delayed rendering of some line with some with some time variable, and the rendering is done with simple with ray merging, where I use AABB, which is the distance to the cube, so you can do cube effects as well. Thank you very much. Of course, I didn't show you like state-of-the-art IQ demo with ray merging and so on, but believe me, just Google for it, you will see this is just amazing what people do and what IQ is doing with this technique, but I will let you discover by yourself. Thank you very much. If you have any questions, then you are welcome. Also, I'm here at the party, so no worries, I'm here. I don't see any questions. Thank you very much. That's it.
Thank you very much, Maku. Thank you for joining us.